Hi friend, welcome to the abstract algebra class. It is class 30. Here we prove the theorem. The necessary and sufficient condition for a finite complex H of a group G to be a subgroup of G is A, B belongs to H. This implies A into B belongs to H. Or a non-empty finite subset of a group which is closed under multiplication is a subgroup of G. Here we want to prove this theorem. First we analyze the theorem proof. Let G be a group, and giving G be a group and H be a finite complex of G. That is, finite complex means H is a finite subset of G. We have to prove that H is a subgroup of G if and only if A, B belongs to H. This implies A into B belongs to H. If A, B belongs to H, A into B belongs to H, it means closure axiom under multiplication. Suppose H is a subgroup of G. We assume that H is a subgroup of G. H is a subgroup of G. This implies H is itself a group with respect to multiplication. It implies when H is a group and two element which is belongs to H, it implies their product also belongs to H. Since H is a subgroup of G, H is a group, then H satisfies closure axiom. It proves the second part of the theorem. Conversely, suppose H is a finite non-empty subset of G satisfying the condition A, B belongs to H implies A into B belongs to H. It is relation 1. We have to prove that H is a subgroup of G. Here is the right side. Here we say that the right side of the theorem is true. We prove the left side. H is a subgroup of G. Here, suppose H is a subgroup of H is a finite non-empty subset of G satisfying the condition A, B. This condition A, B belongs to H implies A into B belongs to H. It is relation 1. We have to prove that H is a subgroup of G. From equation 1, we have this equation we have H satisfies closure axiom. Because A, B belongs to H implies A into B belongs to H. Therefore, A into B it is closure axiom. Number 1, closure axiom. Actually, now here we want to prove H is a subgroup of G. Since H is we want to prove H is a subgroup, then we have to prove that H satisfies 4 conditions. First condition, closure axiom. Second condition, associative. Third condition, identity element. Fourth condition, inverse. First one, from equation 1, conclude that closure axiom holds. H is a subgroup. We know that. Here, H is a subset of G. Then all elements of H are element of G. G is the element of G. G is a group. The element of G satisfy associative axiom. Therefore, element of H also satisfy associative axiom. Here, from here we find second axiom, associative axiom. From equation 1, A, B belongs to H. Here, B we replace B by A, B by A. A, belongs to H implies A into A belongs to H. Implies A square belongs to H. And A square both belongs to H implies A into A square belongs to H. Implies A cubic belongs to H. A cubic belongs to H. Implies A into A cubic belongs to H. Implies A to the power 4 belongs to H. Therefore, A, A square and so on, A to the power n belongs to H. They are infinite number, but H is finite. There must be repetition in the above array of elements. Here, some of them should be equal to each other. Implies a power r equal to a power s for some r comma s belongs to z. Z is the set of integer. Implies a to the power r into a to the power minus s equal to a to the power s into a to the power minus s. We multiply both sides by a to the power minus s. This implies a to the power r minus s equal to a to the power s minus s 0, a to the power 0 equal to e equal to 1 is the identity element. R comma s belongs to a set of integer sorry implies r minus s belongs to z. This implies a to the power r minus s belongs to h. Therefore, a to the power r, a to the power 0 equal to a to the power r minus s equal to e belongs to h. Therefore, identity element exists in h. It is number 3. Number 3, identity element exists. Take r greater than s implies r minus s greater than 0 implies r minus s minus 1 greater than 0 or equal to greater than r minus s minus 1 greater than or equal to 0 implies a to the power r minus s minus 1 belongs to h. Now a to the power r minus s minus 1 into a equal to a to the power r minus s equal to a to the power 0 equal to e equal to 1 is the identity element. This shows that h a belongs to h. H element a belongs to h has inverse a to the power r minus s minus 1 belongs to h. Therefore, it is inverse. Number 4. Actually, we prove that 4 cases hold in G. Therefore, H is a subgroup of G. That is, every element of H has inverse. From here, every element of H has inverse. Therefore, H is itself a group with respect to multiplication, and H belongs to G. Therefore, H is a subgroup of G, which is our I proof. Thank you.